In this video, we'll explore the concept of conditional probability. The big idea is this. Information about or data on one event might change our understanding of another event. Consider an example. Suppose we have a jar of marbles. 1 is black, 5 are blue, and 4 are orange. Then suppose I select one marble at random and I don't tell you what color it is. As a probability expert, you know that there's a 4 out of 10 chance, or a 0.4 probability, that my marble is orange. Next, suppose I accidentally slip, and I tell you that my marble isn't blue. This information shrinks the sample space to only 5 possibilities. Thus, given the information that I didn't pick a blue marble, there's now a 4 out of 5 chance, or a 0.8 probability, that I got an orange marble. This calculation is what we call a conditional probability. The conditional probability that my marble is orange, given that it's not blue, is 0.8. In general, this notation expresses an interest in the unknown event on the left, given the known event on the right, where the vertical line here can be read as given or conditioned on. Zooming out then, the 0.4 unconditional probability of my marble being orange jumped to a 0.8 conditional probability after learning that my marble is not blue. Consider some more examples that illustrate the concept of conditional probability. Suppose you're supposed to get together with a friend and you're wondering if they're tired. They then tell you that they didn't sleep last night. Now pause your video to think about whether this information increases or decreases the probability that they're tired. That is, what's bigger, the conditional or unconditional probability of this event? In this case, the information that your friend didn't sleep increases the probability that they're tired. Consider another example. Suppose you're wondering whether someone owns a pair of ice skates. You then learn that they've never skated before. This information decreases the probability that they own a pair of ice skates. Mainly, a person that you know has never skated is less likely than a random person is to own ice skates. Finally, let's compare two conditional probabilities. First, suppose that you see a car with smoke coming out of the hood. The chance that something's wrong with that car is pretty certain. That is, the conditional probability that something's wrong with a car, given the information that it's smoking, is approximately 1. But swapping the order of these events changes the meaning of this probability, hence its value. Specifically, the conditional probability that a car is smoking, given the information that something's wrong with the car, is approximately 0. So many things can go wrong with a car. The tires could be flat, the headlights might be broken, it might be out of gas, and so on. A smoking car is just one very rare possibility. Zooming out then, these conditional probabilities are unequal. In general, these 3 examples demonstrate the following points. A new piece of information might increase the probability of an event. That is, the conditional probability of A given information B might be bigger than the unconditional probability of A without this information. Or it might decrease the probability of an event. Further, the order of conditioning, that is, which event is known and which event is unknown, matters. It's typically the case that the conditional probability of event A given information B is unequal to the conditional probability of event B given information A. Now that we have a sense for the concept of conditioning on given information, let's explore how we can calculate conditional probabilities in practice. As an example, suppose that a new article is posted on some social media site. Let A be the event that the article is fake news, and B be the event that it has an exclamation point in the title. And let's assume that we have the following background information on these events. There's a 40% chance that an article is fake, a 12% chance that it has an exclamation point in the title, and a 10% chance that it's both fake and has an exclamation point. This information is reflected in the Venn diagram at right. Now, suppose that a new article is posted and you notice that it has an exclamation point in the title. Given this information, what's the chance that the article is fake? That is, what's the conditional probability of event A given information B? I encourage you to pause and try to calculate this probability before moving on. Just as was the case with the marble example, the additional information that the article has an exclamation point shrinks the sample space of possibilities to those that coincide with event B. And notice that within this shrunken sample space of articles with exclamation points B, a large proportion here are fake news. Specifically, the fraction of articles with exclamation points that are fake is 0.1 divided by 0.12, or 83%. Zooming out then, without knowing anything about an article, it has a 40% chance, or unconditional probability, of being fake. But if we learn that an article has an exclamation point in the title, the conditional probability that it's fake news jumps to 83%. Using probability notation, notice that we obtained this figure by considering the intersection of event A with B relative to the shrunken sample space of event B. In general, the conditional probability of the unknown event A, given the information that event B has occurred, can be calculated by dividing the probability of observing event A with B relative to the probability that event B occurs in the first place. Finally, sometimes we're given information about the conditional probability, but not the intersection. In these cases, we can rearrange the formula for conditional probability. For example, let A be the event that somebody has a pet cat, and B be the event that they have a pet dog. Then, suppose that roughly 50% of people in the US have a pet dog. That is, the probability of event B equals 0.5. Further, suppose that 30% of dog owners also have a pet cat. That is, the conditional probability of event A given event B is 0.3. From this information, we'd like to calculate the probability that somebody has both a dog and a cat. That is, what's the probability of A and B? Now, we actually are in luck here. Notice that we can rearrange the formula for the conditional probability of A given B, which we know, to solve for the unknown probability of the intersection. Specifically, the probability of the intersection of A and B is the product of the conditional probability of A given B and the unconditional probability of B. Plugging in our given information across the US, 30% of dog owners have a cat, and 50% of people are dog owners. Thus, 30% of 50%, or 15% of people, have both a dog and a cat.